interior and exterior angles of a polygon. So we know the simplest form of the polygon is the triangle. And we know the sum of the interior angles of the triangle is 180 degrees. Now that was proven in an earlier video, but we're going to use that fact to determine the sum of the interior angles of other polygons with more than 3 sides. So let's first look at the quadrilateral. The trick here is if we want to know what the sum of the interior angles is, we're going to divide this polygon into triangles. Now, how many triangles can we divide it into? The way we do this is pick any vertex you want. So there's 4 to choose. Say we start at vertex where our angle 3 is located. All you have to do is draw all possible diagonals from this vertex. So there's only one, and we have now divided this quadrilateral into 2 triangles. So 2 triangles, each 180 degrees in summation for their interior angles, reveals that the polygon with 4 sides should have an interior angle sum of 360 degrees. Let's move on to a 5-sided polygon, known as the pentagon. Again, pick any vertex and draw all possible diagonals. There's 3 triangles here, each 180 degrees, for a sum total of 540. We'll do one more. Let's say we take the hexagon, pick any vertex we want, draw all possible diagonals. We'll see the hexagon can get divided into 4 triangles, each with an interior angle measure of 180 degrees in summation. So in total, 4 times the 180 degrees is equal to 720. So all hexagons have an interior angle sum of 720 degrees. So what you'll notice is the number of sides minus 2 is how many diagonals you can draw, and also, the number of sides minus 3 is how many diagonals you can draw, and therefore the number of sides minus 2 is how many triangles can be drawn or formed when implementing those diagonals. So if I want to take an n-sided polygon, so pick any number of sides, again, where n is greater than or equal to 3. If the number of sides is less than 3, we don't have a polygon. Then the sum of the interior angles should be the number of triangles I could possibly divide the shape into by implementing diagonals times 180 degrees for each triangle. So how many can we divide it into? Well, it's always the number of sides minus 2 times 180. So there's our formula for the sum of the interior angles. Now, if we have a regular polygon, the measure of each individual angle will be the total sum divided by however many angles there are. How many angles are there? Well, there's the same number of angles as number of sides. So if n represents the number of sides, then we can say each individual angle can be calculated by taking the sum, dividing it by the number of angles. So n-sided, n angles. So this is our formula for a total sum of the interior angles. And here's our formula for the measure of each individual angle as long as it's regular. If it's irregular, we can't just divide by n because not all of them are the same. So that is interior angles of the polygon. Now what about exterior angles? So what does this tell you? Actually, before we move on to exterior, the interior, what that tells you is not all polygons have the same sum for their interior angles. It all depends on the value of n. Okay, so you would want to pay attention to that. Whatever the number of sides are, subtract 2 and multiply by 180. Now, when it comes to the exterior angles, let's take our triangle. We extend out our sides. what is the sum of these angles? Or if we look at quadrilateral and we extend out, or a pentagon, well, you want to imagine, and if I had an animation, I would implement this, but imagine if we brought all those vertices in each triangle, in each polygon, and collapsed them into a single point. So we brought these in to a single point through collapsing them in. The number of spokes coming out of that single point is going to be equal to the number of exterior angles. They all meet at this common point, and therefore, the sum of the exterior angles always makes a full revolution, which is 360 degrees. So when you collapse all of those points in on a singular point, when you add together those exterior angles, it always totals 360. Now we could put a little math behind this, so let's look at the triangle example. I'm going to label the interior angles A, B, and C. So here's what we know. We know that A plus B plus C is equal to 180. We know that 2 plus B is equal to 180. We know that 1 plus C is equal to 180. And we know that 3 plus A is equal to 180 because these are linear pairs. And this is because of the sum of the interior angles, which we discussed at the beginning. Now, if we take these three angles, 1, 2, and 3, and add them in to that equation, so we have 1 plus 2 plus 3 plus A plus B plus C, each time we add those in, on the other side, we want to add in the equivalent to the other side, which would be for 2, if we manipulate that, it's going to be 180 minus B. So I've added in the equivalent to 1 on the other side. So again, this is the equivalent to 2, this is the equivalent to 1, and this is the equivalent to 3 based on our linear pair calculation. And all we did was add 2 plus 3 to the left side, so we have to add the equivalent to the right side. Now we're going to clean things up because we ultimately want to know what is 1 plus 2 plus 3, because that's what the exterior angles should be. So on this right side, 180 and 180 is 360, plus another 360 is 720. Now I'm going to move the A, B, and C to the right side. So we're going to have minus 2A, minus 2B, minus 2C. Now if we factor out a negative 2, we have A plus B plus C. Well, we know what A plus B plus C is. That's 180. So 720 minus 2 times 180 is 360. And therefore, I already moved this A, B, and C to the left side. So 1 plus 2 plus 3, 1 plus 2 plus 3, and 1 plus 2 plus 3 equals 360. So it equals 360 for the triangle, but does it equal 360 also for the quadrilateral? So I'll do it one more time with the same process to reveal that it's also a sum of 360 for the exterior angles of a quadrilateral, and then I'll leave it up to you if you want to verify whether or not polygons of more side lengths than 4 also sum to 360. But it does in fact work. All polygons, their exterior angles sum to 360 as long as the exterior angles are formatted in the same way. So we'll do A, B, C, and D. So here's what we know. A plus B plus C plus D is equal to 360. So remember, n minus 2 times 180 is 4 sides, so 2 times 180 is 360. So that comes from the interior angles. We also know A plus 1, B plus 2, C plus 3, and D plus 4, these all equal 180 because they're linear pairs. So what we can do is add 1, 2, 3, and 4 to the left side and add their equivalents to the right side in the terms of 180s in the A. So we're going to do 1 plus 2 plus 3 plus 4. Or if we want, we can make this even simpler. So I'll show you another way. We could do, let's move A, B, C, D to the other side of these equations. Actually, we would want to add them all together. So we're going to stay with that. 1 plus 2 plus 3 plus 4 plus A plus B plus C plus D is equal to 360. And then we're going to do plus the equivalent of 1, which is 180 minus A, plus the equivalent of 2, which is 180 minus B. And all I'm doing is taking those linear pair equations and solving for 1, 2, 3, and 4. I'm going to do plus 180 minus C plus 180 minus D. So on this right side, we're going to have 720, because 180 times 4 is 720, plus 360 is 1080 minus A minus B minus C minus D. If we subtract A, B, C, and D, we're going to get 1080 minus 2A plus B plus C plus D. So we subtracted A, B, C, D from both sides. So 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3 plus 4. So A plus B plus C plus D is 360 times 2 is 720. So what do we get again but 360? So again, implementing another side does not change the sum of the exterior angles. And you can do the same process for a 5-sided, but at the end of the day, let's make the note. Exterior angles, sum to 360 degrees for an n-sided polygon. So that's why it's a little different than the interior angles. So the interior angles depends on the number of sides. The exterior angles is always 360. So there's a video on interior and exterior angles of polygons.